Welcome friends, we are on in the 90th module of AI now. We'll be talking about game playing algorithms now. Game playing is one of the most coveted area of research, and it's very attractive in terms of revenue generation as well. So a lot of people are working in this direction. Game playing itself is an AI domain, and we'll be talking about why game playing is an AI domain, what are the problems, and what are the solutions. This module and few subsequent modules will be looking at the problems and the solutions. Okay, we'll begin with the introduction about game playing algorithms and some history and a few other prerequisites that one would like to have before embarking on game playing. There's a lot of success in research and commercial field. It's very interesting. It's also a very structured domain. What does that mean? A structured domain, because we know start state. Every game we are very clear about the start state. We are very clear about the end state. We have already seen the example of chess. Not only that, the rules are very structured, because people are playing and winning and losing. The rules are very well defined in most cases. Pick up any game and you have very clear idea about those rules. So this is the third characteristic which is very important for us. But then they interact with humans. A chess playing program interacts with human. A card playing program interacts with humans, and we want that program to act like human, and that's where the AI comes into picture. Okay, usually you have two problems, two things which are associated with such programs. One is called plausible move generator. Take the example of chess. When you look at the chess board, there may be hundreds of moves possible, but will you think of 100 moves? You only think of few, 5, 6, 7, max 10 moves, not more. How have you shortlisted those moves? We don't really know, but there is something which we do. Over the period of time, we are doing it. In fact, there is a structured process. This is not like neurons, there is a structured process. When you start learning it, playing chess, you probably, every rule is to be reminded, like the knight must work this way, rook must proceed this way, and so on and so forth. So that doesn't happen automatically, but over a period of time, you learn the rules of playing and then generate your own rules, your heuristic rules. You become an expert of playing chess. So there are a lot of heuristics involved. Like always, for example, if there is a player who is very good in playing something called threat of fork, then you should learn to be aware of that every time you play chess with him. We'll learn about threat of fork later. In later modules, we'll be discussing about that as well. Point is, we generate those rules. Those rules are based on domain knowledge. So based on domain knowledge, we know that out of 100 rules, only 10 rules, 10 moves are important, and we only focus, we only compare those rules and choose the best out of it. So that's the first thing that we'll do. The second thing is, once we apply that thing, and eventually we get some options of the end state, we'd like to compare those end states as well, and we'd like to figure out which end state is better for us, and we should choose a path which leads us to that state. Okay, so again, a kind of heuristic function. It's called static evaluation function, which is to be applied to those states, and looking at the states, the static evaluation functions value, will be able to determine whether a state is good or bad, how good that state is, whether should I go ahead with this move which results into this state or not, and all that. These two things are something which are very important for a game playing program, but both of them are based on domain knowledge. They are specific for specific game. For chess, it is different than some other game. Okay, but then there are few things which you can generalize. For example, how you move around in state space. Now this is not similar to the examples that I've seen. There is some difference which we are going to see, highlight, and see how we can manage. But then that part, search part, is possible to be managed very easily, and it independent of any game. Okay, and we'll be concentrating on that in subsequent modules. Advantage of game is obviously there are quite structured rules. Okay, which whenever you cannot move a piece without the rule. Okay, for example, we have a rook. In front of it, we have a pawn, and I can't move this rook further unless this pawn is not there. Okay, I'll have to remove this pawn only then. The rule is that I cannot do it. Except knight, no other piece can move forward. Okay, we know this. Oh, this is the rule. Okay, so obviously, if you believe that playing a game is simple, chess is hard. But if you pick up some simple game, even tic-tac-toe, zero and cross, not and cross problem. That also is not that simple. Okay, if you have tried writing a program for it, you probably realize that it requires a lot of complexities. And we'll be talking about that. One of the major problem with this kind of a problem is that the permutation and combination is too huge, and it would be impossible for you to explore the complete game tree in given time. That is good also, because if you completely explore the game tree, you know exactly which path to follow, and once you reach there, you won. So you know exactly whether you are going to win or not, and there is no charm in playing that. Okay, so that's in a way good for the game playing programs. Current era, mobile and multi-agent games are also in high demand. But again, once we study all this, you realize that this is also going to be an extremely important core component for those games as well. There are some issues, especially one issue which I would like to highlight is that if you have a multi-agent game, many complexities related to multi-problem exist. For example, if two cars are racing, now two players cannot use the same lane to drive their car. Okay, so that is one thing. Okay, it's called synchronization. Or both of them cannot park the car at the same place. So that is a problem. That is something which is additional to what we are going to discuss. But otherwise, all conventional game playing issues are there, and what we are going to discuss is relevant for all of them. Plausible move generator, which I talked about, which remember we only, as I said, we have 100 odd moves and we are only concentrating on 10 out of that. Now that is also not all that specific. This is also very, very dynamic. Dynamic in the sense that it depends on many things. First, whether it's a starting part or the ending part of a game. Usually starting and ending part, you don't need to worry much about plausible move generators, but the middle part you need to. Second is criticality of the game. Suppose your king is under attack. If the king is under attack, you will have to look at more number of moves. You cannot just concentrate on 10. You will have to look at more number of. It is critical, and so on and so forth. So there are multiple issues which let you decide which kind of plausible move generator should be used and how dense it should generate. Remember our discussion about scarce neighborhood and dense neighborhood. Here PMG also works in the similar fashion. Generally it uses scarce neighborhood, but in a critical condition it goes for the sparse the dense neighborhood function as well. But okay, there is one important thing which I would like to also highlight, the difference between plausible move generator and a legal move generator. A legal move is legal because you can play it, but plausible move is legal, but then will not lead to anything significant. We will not explore it. For example, moving up on further is a legal move, but it doesn't add any value to our case, then what's the point in doing it? So plausible move generator will not explore those moves. So legal moves are all possible moves. Plausible moves are only those moves which make sense in current situation. There is one more move called winning move. Winning move leads us to win. Now this is an important category because we want winning moves to be executed out of those plausible move generators. Plausible moves may lead to a defeat. We may pick up one of the moves from plausible move generator list, but eventually we lose. It is possible, but winning move is something which. So again, these are subsets. So legal moves, then a subset of it are plausible moves, subset of which are winning moves. The advantage of plausible move generator is that we can probe much deeper, because if we have 100 odd moves to consider, and if you have say 5 minutes or 6 minutes or some time, we have to have 100 options to explore. We will not go much deep. But if it reduced to 10, we can go much deeper. Commercial chess programs go 15, 20 plies deep, 15, 20 levels deep. And this is a huge thing, okay, just because they use this plausible move generator. If plausible move generator is not used, this probably would reduce to 2-3 levels or 5 levels max. One more interesting thing is I was talking about the initial and end part of the game. Again, because we have the time constraints in most of the games, including chess, we would like to finish that part faster, the initial part and the later part faster, which we can do by doing a simple trick. We decide that for a given move, this is the best move, and store it in the database. We don't do anything. We don't apply search. We don't apply heuristic and anything. We know that if the player, and if you have seen chess champions playing the initial part of the game, you probably have seen they're doing it so fast. They start moving their pieces very, very fast. They would like to do it faster, because that in the initial game, you know that if opponent is playing this, I'll have to play this, and so on and so forth. It is not very complicated. So that thing is stored in the database. So initial part is stored in the database, and that thing is known as a book move. Okay, that move is stored in the database. So whenever opponent plays that, you just match that thing in the database and generate. Book moves can be huge, but then there is an advantage. Okay, you just forego all the search, and the other thing is going to work. They are quite useful for the beginning and ending part of chess, and most of them are used actually. But you can't use book moves from the middle part of the game. And why? Because we know that on an average we have 35 as a branching factor in game, and on an average a player plays 50 moves in a game. Considering both players, you have total 35 raised to 100 possible moves. Now you can't explore that search space in real time. So it is impossible for us, or you can't even store that. You can't even have the database to store that. Large database is almost impossible to achieve, and searching in the database also is too expensive. So it is just impossible. So you can't use book moves for the middle game. That those are only used for beginning and ending games. Okay, here as I said, there's one more thing. Heuristic function is used, named as a static evaluation function. What we do is, given a point, we explore the tree as long as we can and come back and choose a move. For every, suppose you have 4 different alternatives, we try exploring each one, look at what it offers, and pick up the base node. This is the general process. Now, let us talk a bit about the history of game playing programs. Claude Shannon talked about game playing programs long back in 1950. And then Alan Turing also said that it is possible to build a chess playing program, and provided description of that program as well. He didn't try building it himself. Samuels built checkers program in 1960, and that checkers program used to play that draught game or the checkers game. That game was, and that was a real good example of how one can design a game playing program. That program, one of the great ability of that program to learn on its own, learn from the experience. It eventually becomes so good that it could actually beat the inventor Samuel himself. Long back in 1989, a computer from IBM called Deep Thought defeated Richard Levy, champion, Olympic champion then. Then there was a Deep Blue in 1996, beaten Garry Kasparov, world champion then, 3-2, by 3-2 margin. They played 5 games, 3 won by Deep Thought, 2 by Garry Kasparov. And then there was one more program called X3D Fritz that also played with Garry Kasparov recently in 2003, comparatively recently, it's 13 years before, but it's still quite near compared to other. So that drawn level with Garry Kasparov. Okay, so that was again an excellent example. So this is an history. Stanford University is so interested. They are running a program. They provide a game playing platform where people can use that platform to build their own games, and then they compete. And they till 2005 they are running a program, running a contest where people can write their program and demonstrate their program, and they organize the contest in the end and declare winners of that contest and all that. There are a lot of multi-agent games are also happening over internet. But then we before we go further, we have to have one more important thing. What are the types of game we are interested in talking about? There are a few ways to classify games. We have a single person game. Solitaire is one example. 2-person game is chess. Multi-person game, multiplayer game like car racing is the other example. So this is one way to differentiate. One more way is whether the game is zero sum. A zero sum game is one's gain is somebody else's loss. So if I get something, somebody else will lose. Many card games are like that. If I get more hands, other parties will get lesser. Okay, so such games are called zero sum games. In some games it is not so. For example, in car racing, if I collide with somebody else, both of us lose points. Okay, my loss is not his gain. Or some marketing game where it is possible for many of us to profit. If everything is fine, everybody is playing well, everybody will profit. That's an example. The third way to differentiate is whether the complete information about the game is available. card games you don't have complete information. Now you may understand that is something similar to the discussion about agents that we had before, and it is true. Complete information games are easier to program. Incomplete information games require assumptions to be made and revert those assumptions. Okay, that requires that NMRS and all that we have talked about will come into picture, which is more expensive in terms of time as well as storage. Okay, complete information includes the environment as well. It talks about, for example, a car racing game, what others are doing, that information is also available with you. If that is available with you, only then you will be able to do it well in car racing. If you don't know what others are doing, probably you will not be able to do, probably you will be able to collide, you will soon collide with somebody else. So complete information games are comparatively better, but not incomplete information, when you don't have complete information, as I said, you require assumptions and all that. So that makes it a little harder. The last way to differentiate is whether it is deterministic. For example, if I make a move, can I say that if I make a move, I will get this result for sure? If I am not sure, it is non-deterministic. If it is sure, it is deterministic. For example, I am playing an 8 puzzle. I know I move a slide down, I know exactly what will happen. Or if I have some series of movements, some series of actions, I can calculate the output now and I will have the same output, that is not going to change. In case of car driving, you cannot have it, or even in chess. So these are the points about determinism, because in chess it is little more deterministic than car racing. Why? Because it only requires the opponents that thing, but your case you know exactly what is going to happen. If opponent is not going to play as per your that thing, that part will change, but you know when I am placing a piece forward, it is going to go forward. Okay, so that part is there in your hand, so that part is deterministic. In case of car, it is not so. In car racing, you press the accelerator pedal, but might not work because you already reached the maximum limit. So it's not all that deterministic. Not only that, you can't, because there are a lot of other players are also involved, so it is not that deterministic. Obviously, you have to have some assumptions in this case. In case of 2-player game, what we are going to do here, or for our case, we'll pick up a 2-player game. We'll describe all subsequent modules with only assumption of 2-player games and complete information games. We are not going to look at that part. That part is little more complicated. We require some other, as I said, those assumptions and that thing. We'll refer to hidden Markov model at the end of this thing when we talk about machine learning, how that can be addressed. So we'll throw some light on that, but otherwise we'll not be looking at incomplete information games. Okay, 2-player game can always be extended to multiple agents. Only the issue is that synchronization, which I talked about, that can be added. And also we assume that both of the opponents, their goals are completely opposite. So my win is the other person's defeat and his win is my defeat. Okay, it is not that both of us can win. Okay, that kind of a situation we will not be talking about. So a game tree is a search tree, but then unlike the conventional search tree, the layers are different. The first layer, if I'm playing the first move, I call it max, because I'm going to maximize my chances of winning. Next level is played by the opponent and is going to minimize my chances of winning. Again, next level is my own, where I'm going to maximize my chances of winning. So that's why they are called min max layer. The max layer is the layer where the player plays, and min layer is where the opponent plays. So there may be multiple outcomes. In case of tic-tac-toe, 3 possible outcomes: win, lose and draw. So tic-tac-toe is shown on the screen. There are 8 different ways of winning. What you want to achieve is 3 consecutive cells and you mark, okay, and if you mark 3 consecutive cells, you winning. So there are 8 different ways of winning shown on the screen. And also there is one more figure which describes the complete search tree. Not complete, is also a very small subset of it, and we are not exploring every child in every this thing. We are only exploring one child in every layer, obviously because of the space constraint on the screen. But even if there is no space constraint, it's going to be a huge thing even in this case. But then look at some of the states which are encircled. Okay, 1, 2, and there is something called W, there is something called L. Now this 1, you can see that I have 2x in the same line, but then there is 0 played. Okay, and the other one, you have 2x in the line where 0 is played elsewhere. Now what is the difference between these two? When 2x are in line and when 0 is placed next, I am preventing that person from winning. and when I place 0 somewhere else, I am not preventing, I am making sure that I lose. Okay, so that is where it is, and you can see that this results into win or lose based on that information. Okay, so W is winning, you can see that all 3 X in a line, so we are winning, and when 3 zeros are in sequence, we are losing. So there is one which is W, which is we would like to reach to a state which is W, okay, and we would like to avoid states which are L. If we don't get W, we may be satisfied with D, which is draw. In this particular case, you can see that it is possible, and because it is such a small program, the problem space, the state itself, I have actually drawn all of them. In case of chess, like I can't even draw this, but you can easily understand that there are 3 possible outcomes here: win, lose, and draw. So you can see that there are some cases where nobody is winning. None of them get that thing in sequence. So that is a draw. And there are 3 less choices for a second player, which you can also see. Now with that, we'll come to an end of this particular module. What we have seen in this module, we have just begun talking about game playing. We have looked at some theories, and we have looked at plausible move generator. We talked about static evaluation function. We looked at the history of the game playing algorithms. We have looked at a search process which requires minimum and maximum layers. Minimum layer, the player is playing, maximum layer the player is playing, the minimum layer the opponent is playing, which is going to minimize the player's chance of winning. And with this note, we'll end this session, but this is going to be the prerequisite to the subsequent modules, where we are actually embarking on learning about game playing in a little more depth. Thank you.